Okay, so today I would like to talk to you about a large X-ray survey that we have performed with XMM-Newton in the prime parts of the LSST Deep-Drilling Fields. The survey is named XMM-SERVS, and it was designed primarily as an AGN-driven survey, although it is also certainly powerful for studies of clusters and groups, and starburst and normal galaxies and stars and other cosmic X-ray sources. And a large team of us listed here has been working on this survey for the past several years. I would especially like to highlight the heroic efforts made by my Penn State students and postdoctoral researchers, several shown here along the left, who have done a huge amount of work on XMM-SERVS now, often working under very difficult pandemic conditions as the XMM-Newton and multi-wavelength data were incoming. We have released public X-ray source catalogs now for XMM-SERVS, and we are in the scientific exploitation phase, the best phase perhaps. And we are also, of course, actively getting ready for LSST as part of doing this work. And then at the end of today's talk, if there's time, I would also like to briefly describe a NASA MIDEX mission currently in phase A that would greatly extend surveys in the LSST deep drilling fields. That is the STAR-X mission. I'll briefly advertise that mission if there's time. And so let's get on with it. So XMM-Newton is a very powerful X-ray survey machine for the reasons listed here. It's large effective area, it's good field of view, good angular resolution, and broad bandpass. And it's particularly powerful in the moderate depth regime where we've used it for the XMM-SERVS survey. And of course, now that XMM-Newton has been operating for more than 23 years, it's worth taking on some large and aggressive projects with it. And so we designed a project to complement the Rubin Observatory's legacy survey of space and time. Okay, here's a recent picture of the Rubin Observatory. It is aiming to begin the LSST in early 2025. The main LSST survey will be over 18,000 square degrees of the southern sky. But very importantly for XMM-SERVS is that about 10% of Rubin's time is going to be used to conduct a set of mini surveys, including 5 deep drilling fields. This plot here shows the overall coverage planned for the LSST. And of course, Rubin's field of view is 10 square degrees. And so it has a set of deep drilling fields, each one of which is 10 square degrees. Cosmos, XMM-LSS, Chandra Deep Field South, and Elias S1, except for the Euclid Deep Field South, where they're in fact doing 20 square degrees at half depth. And Rubin is likely going to be observing these deep drilling fields very intensively, both in terms of temporal coverage and in terms of ultimate sensitivity. They are aiming to cover these deep drilling fields every 2 to 3 nights in the GRIZY bands over the 10-year survey. Now, different parts of these deep drilling fields have different quality multi-wavelength data, at least presently available. For example, the famous Cosmos survey has its best coverage over 2 square degrees of the 10 square degree deep drilling field. And here listed are all of the Rubin deep drilling fields with some of their details. And for these 3 fields, the 3 here on the left, there are areas known as the SERVS areas, which stands for the Spitzer Extragalactic Representative Volume Survey, that have truly superb multi-wavelength data. In particular, there's about 3.2 square degrees in Elias S1, 5.3 square degrees in XMM-LSS, and 4.6 square degrees in Deep Field South that have superior multi-wavelength data. And those are the regions that we targeted with this XMM survey. Here, these plots just show some of that multi-wavelength coverage. The various colored shapes show various multi-wavelength surveys, and we targeted these SERVS areas that have the best multi-wavelength data, which immediately allows us to start doing exciting science with the X-ray sources. Okay, so here is a quick summary of the 5 megasecond XMM-SERVS multi-year heritage program. We have, again, covered 5.3 square degrees with XMM-LSS, 4.6 square degrees in Deep Field South and 3.2 square degrees in LSST. And we have achieved uniform 50 kilosecond XMM-Newton depth in these regions. The uniformity was possible because we adopted a two-stage observing approach where we observed them the first time, and then we went back, we reserved some time and went back and filled in holes due to background flaring, and that let us get quite good uniform coverage. And the 50 kilosecond depth allows us to get sufficiently deep to capture a large fraction of cosmic accretion power, about 70% of cosmic accretion power we cover. And because here we have three fields, and then if you add Cosmos, which would be a fourth field, each one of which is fairly large on the sky, sufficiently large to cover a good sampling of cosmic large-scale structure. One of the things that we can do with XMM-SERVS is use it to investigate the effects of cosmic large-scale structures, ranging from voids up to superclusters, on supermassive black hole growth in the universe. And we have now detected about 10,200 AGNs and many X-ray groups and clusters in XMM-SERVS. Here, for example, is the beautiful XMM-Newton panoramic coverage around the Chandra Deep Field South. So here is the original super deep Chandra Deep Field South coverage. And Chandra Deep Field South serves as an ideal calibration field for XMM-SERVS, although, as you can see, it only covers about 1/35 of the panoramic coverage that XMM-Newton has given us. And for comparison, here's the size of the moon on the sky. And then here are all of the fields put together. Again, Chandra Deep Field South here. Here's XMM-LSS. That original X-ray cataloging work was led by Chen-Ting Chen. And then here is LSST. And the cataloging work on Deep Field South and LSST in the X-ray with XMM-Newton was led by Qingling Ni. And about 88% of the X-ray sources that we've detected in these fields have solid multi-wavelength counterparts. That's possible due to the impressively deep multi-wavelength coverage that we targeted in these particular areas. You go outside those areas, the multi-wavelength coverage is a lot worse. But in these areas, you can do a very good job on the multi-wavelength coverage and the source identification. Here is a plot that just sort of shows solid angle versus exposure time, and it compares XMM-SERVS to XMM-Cosmos. And of course, XMM-Cosmos in its own right is a very powerful X-ray survey. Here it is, and here is XMM-SERVS. So you can see it really is taking these sort of several square degree surveys, to the next level. It represents a large increase over, for example, XMM-Cosmos. Here is just a quick summary of the numbers of sources detected. For all three of the XMM-SERVS fields together, we detected about 11,900 X-ray point sources. As I said, 10,200 of those are AGNs, about 2,800 are type 1, about 7,400 are not type 1, non-type 1 AGNs. And then we have about 1,250 galaxies and 450 stars. And, for comparison to, eROSITA, which of course is doing fantastic survey work right now as well, well, the XMM-SERVS point source density is about 910 per square degree, nearly 1,000 per square degree, compared to, eROSITA, where they're down at about 170 per square degree typically. And of course, also the XMM-Newton source positions are considerably better, which is extremely helpful when trying to get reliable multi-wavelength counterparts at these fainter X-ray flux levels that we're sampling relative to eROSITA. We have done a lot of work getting all of the multi-wavelength data in order, analyzed all systematically. We have used Tractor. Our team has used Tractor to do systematic band-matched photometry. And we have used these photometric data to then derive photometric redshifts. Here, for example, are results showing 800,000 photometric redshifts we've now derived in Chandra Deep Field South for the X-ray sources and all the non-X-ray sources as well. We do them all in one shot using all these multi-wavelength data listed here. And then similarly, we have about 1.2 million photometric redshifts in XMM-LSS, again, using these multi-wavelength data listed there. Okay. And then in terms of spectroscopic and photometric redshift completeness on the X-ray sources, well, these are the current results. These show sort of the cumulative number of sources for just two of our fields, Deep Field South and XMM-LSS. And you can see that the spectroscopic, there are an impressive number of spectroscopic redshifts already available, listed over here in these two tables. But then if you add in all of the photometric redshifts that I was just describing back here, we actually have, if you look at the combination of spectroscopic and high-quality photometric redshifts, we have 70% of the X-ray sources already having spectroscopic or high-quality photometric redshift. So we have pretty good redshift completeness already, and as I'll talk about in a little bit, that will get much better soon. Okay, here are the current redshift and luminosity redshift distributions for the X-ray AGNs. You can see that we have good numbers of sources, large numbers of sources out to redshifts of about 2 or so. And then we have this tail extending out to redshifts of about 4 and perhaps even beyond. And then down here is luminosity versus redshift. And our sources sort of fill up that part of the diagram. And again, you can see our sources are the gray colored ones. You can see we have very large numbers of sources compared to any of the past surveys, like Stripe 82X and so on. Okay. Now we then have also utilized all of the multi-wavelength data ranging from the X-ray out to the far-infrared to derive spectral energy distributions. Fan Zhao did a huge amount of work on this project, and this was using the Segal code to fit the SEDs. Here, the XMM-Newton data helps substantially in setting the level of the X-ray component and unconfusing otherwise degenerate SED fitting solutions. And so the SED fits have helped a lot in classifying sources into galaxies versus AGNs versus various exotic galaxies like bursting and quenching galaxies and so on. And then the SED fitting, of course, also allows improved source classification, as I just said, and measurements of galaxy properties, things like stellar masses and star formation rates. And in fact, FAN has now done stellar mass and star formation rate measurements for like 2.8 million sources, including, again, all the X-ray sources, as well as all the non-X-ray sources in these fields. And this is very valuable for investigating relations between galaxy growth and black hole growth, which is things we're working on now. So here, for example, just shows our use of calibration off the deep, small regions like the Chandra Deep Field South proper. And you can see that in XMM-SERVS, we do a quite good job recovering stellar masses using the general wide field XMM-SERVS data compared to the ultra deep data that's available in just a little Chandra Deep Field South over like 1/35 of our field. And you can see we do a quite good job recovering stellar masses, and our star formation rates are also quite good. And then in terms of other science projects we've been pushing forward, well, Vivian Yan has done some nice work looking at highly obscured active galaxies. She has done this using direct spectral fitting of the XMM-Newton data. She's spectrally fit all the X-ray sources to select out the ones that appear to be highly obscured based upon their X-ray spectral properties. She has also looked at, for example, correlations between X-ray and infrared luminosities. The sources lying here far below the general relation for AGNs tend to be the very highly obscured ones. And we've also, of course, utilized the SED fitting mentioned back here to also find the highly obscured AGNs. And as you can see from this table down here, we've found a large number of Compton-thick and heavily obscured objects, like 22 Compton-thick AGN candidates, like 137 heavily obscured AGN candidates that we're currently, investigating further. And you can see Vivian's paper for a lot more details on that. Also, Fan Zhao, who I mentioned before, has also done some nice work recently investigating dwarf galaxies containing AGNs in XMM-SERVS. Here, we have now found 73 what we think are quite robust candidates for being dwarf galaxy AGNs at redshifts of 0.05 to 1. These are the blue dots in this diagram of luminosity versus stellar mass. And this is the largest X-ray selected sample of dwarf galaxy AGNs beyond the local universe. That's possible, of course, due to the very impressive sampling ability of XMM-SERVS. Notably, few of the dwarf galaxy AGNs are X-ray obscured, despite the fact they have relatively low luminosities often. And we also have utilized these data to set the best constraints upon the AGN fraction, reaching down to very low stellar masses. You can see Fan's paper for details, but here are plots showing the active fraction and how that depends on stellar mass for either luminosity-based criteria or Eddington ratio-based criteria. Okay, and then also I want to mention that Shifu Zhu, who has done a lot of work on radio AGNs in my group, has performed radio AGN selection and then, comparison with the X-ray data. Shifu has used the Atlas, VLA, and MIDI data that are presently available in these fields, which are very effective for selection of at least highly radio loud or radio loud in general type AGNs. Shifu has utilized a combination of morphology, radio spectral index, and radio excess to select the radio AGNs. Here is a plot that shows, for example, the sources that have very large radio flux excesses compared to their 24 micron fluxes tend to be the ones that are AGN. So he's selected a large sample of 1,815 radio AGNs, and notably the majority of these are not X-ray AGNs or mid-infrared AGNs. And this is expected given what we know about the AGN population from other fields. But now we have a good complete sample of X-ray AGNs, mid-infrared AGNs, and now radio AGNs, giving us complete sampling of the AGN population in the LSST Deep-Drilling Fields. And this will be, of course, extremely valuable once Rubin switches on. I'll say more about that soon. Okay. We have a number of additional XMM-SERVS projects underway and planned. We are currently working to select high redshift AGNs. We have a number of candidates there. These are X-ray sources that have the colors indicating they're very high redshifts, and we aim to follow those up soon. We are looking at supermassive black hole galaxy connections, as I mentioned. We're looking at supermassive black hole growth as a function of cosmic environment. We're looking at the clusters and groups. And then we also have a lot of ongoing work on general spectroscopic follow-up coming in the near future. I'll say more about that in a slide or two. And I just want to highlight that, of course, this was a multi-year heritage program with XMM-Newton, and XMM-SERVS, I think, really will have a superb multi-year heritage. It has, for example, great legacy value as I said, LSST and also dark energy survey deep drilling fields. And so XMM-SERVS is providing a ground truth X-ray AGN sample that we aim to use to calibrate the selection of AGNs in the LSST data, first in the deep drilling fields, and we'll then take what we learned from the deep drilling fields and apply it to the main survey. So in fact, I think much of Rubin AGN selection is ultimately going to be built upon this XMM-Newton AGN sample that has been provided now. And in total, with Rubin, we aim to detect tens of millions of AGNs, and we're going to optimize all that, again, based upon the XMM-SERVS sources and the other AGNs we found in the deep drilling fields. As I mentioned then, these fields are also being targeted with massive spectroscopic programs by MOONS and PFS and Foremost. In fact, this plot here shows a bunch of the complementary multi-wavelength data flooding in for XMM-SERVS. The Devil survey has already performed a lot of spectroscopy, but deeper spectroscopy will be coming soon from MOONS, from PFS, and from Foremost waves. And so those will be very exciting. And in fact, I'm a member of the MOONS project, and we have strong interest in targeting many of the X-ray sources with MOONS. And in fact, a large number of the X-ray AGNs from XMM-SERVS happen to lie in the prime MOONS redshift intervals that they're targeting of 0.9 to 1.7 and 2.0 to 2.6. You can see we have large numbers of AGNs. In fact, we're peaking in that range. And the AGN sky density should not overly perturb the general MOONS galaxy survey. And of course, focused targeting of our X-ray selected clusters and groups with MOONS will also be worthwhile. So MOONS is a very exciting survey, as are these other ones, for doing a lot of the massive spectroscopic follow-up that is required. Also, there are multi-object spectrograph or reverberation mapping campaigns, either that are ongoing or that are coming soon in these fields. For example, the Sloan Digital Sky Survey, as part of its 5th iteration, is performing reverberation mapping to measure direct black hole masses in these same fields. So we'll have direct black hole masses from reverberation mapping in these fields to compare with all the other fantastic multi-wavelength data. And then in the Submillimeter and radio, well, these fields are also being targeted intensively with TolTEC and ALMA and Meerkat and so on. And so there's a lot of exciting possibilities of putting together the long wavelength emission properties with the X-ray properties as well. And let me then say finally that I think XMM-SERVS, in fact, should have, as I mentioned, again, a many-year heritage. It's going to be hard to surpass XMM-SERVS until we have Athena or STAR-X. In fact, I'll say more about STAR-X in just a little bit if there's some time. In fact, let's do that now. So that I've now summarized XMM-SERVS. It's been very successful so far. The science is ongoing. And of course, we have desires to take this even further in the future. And there is a mission called STAR-X, which is the Survey and Time Domain Astrophysical Research Explorer. This is a NASA MIDEX mission. It's currently undergoing a phase A mission concept study. And if selected, we're in competition with one other mission, but if selected, it would launch in 2028. And STAR-X carries an X-ray telescope that covers a very wide area, 1 square degree, and it uses a Wolter Schwarzschild design to maintain very high quality X-ray imaging over that wide field. And then it also has an ultraviolet telescope covering a very wide field as well, which is also quite powerful. So it gives you both X-ray and ultraviolet capabilities, both mounted on an agile spacecraft like Swift, which of course has been wonderfully successful. And in total, STAR-X, in terms of its X-ray survey capability, offers a unique combination of large field of view, large effective area, excellent imaging maintained across that large area, and a low background. It will be in a low Earth orbit. And this should make it an extremely powerful X-ray survey machine. Here is a plot just showing many of the typical numbers for STAR-X. I won't try to go through all of these now because time is limited, but you can refer to this later if you have interest. And there's a lot of science, of course, that STAR-X will do. In terms of time domain studies, there's a great deal of interest in doing time domain studies of supernovae, of tidal disruptions of stars, and of AGN accretion flows via X-ray ultraviolet reverberation mapping. And then on the survey side, there's a lot of interest in studying protoclusters, including the obscured and unobscured AGNs in those protoclusters, investigating high redshift clusters generally, and then targeting high redshift AGNs, where it should be very effective. And in fact, a large fraction of STAR-X's time, about 63%, is planned to be dedicated to time domain surveys. The other 11% or so, and then aside from various other programs, would be dedicated to time domain follow-up. And so I want to focus on the time domain surveys here. So STAR-X would essentially work a lot like the Rubin Observatory in that it would build up very deep surveys episodically via large numbers of shorter observations. So you're accomplishing the time domain science and the survey science all as a part of a single observing program to some significant extent. And for example, with the deep surveys with STAR-X, well, they aim to observe these in a daily fashion over about 13 square degrees. And in total, if you did about 1,500 second observations with a daily cadence over a 2-year period, you'll build up to about a 1 megasecond exposure, reaching about 9 times 10 to the minus 17. That's about 25 times deeper than XMM-SERVS, and it's roughly comparable to about 100 Chandra deep fields at the 1 megasecond Chandra level. And so here you could essentially take all of the XMM-SERVS area and turn it into Chandra deep field depth, which would be wonderful. And in fact, the STAR-X deep and medium surveys are indeed going to likely target the LSST Deep-Drilling Fields extensively. The medium survey then would be observed weekly, and it would be covering about 350 square degrees, reaching, again, very impressive depths, about 5 10 to the minus 16. And this would be comparable to like 175 Chandra cosmos fields. So the combination of the STAR-X deep surveys and medium surveys would be extremely powerful. And we're hoping, this mission will be selected because this could be a very exciting new opportunity for X-ray astronomy in the not too distant future. So I will wrap up there. Thank you very much for your time. And again, if you have interest in using the XMM-SERVS data products, they're all available at this website. Thank you very much.